Okay, good morning, everybody. We have an action-packed week for you. These are the final 4 lectures before we get to the heterocyclic millionaire, which will not be public. And in these 4 lectures, roughly, I would say there's probably 60 or 70% new content, including 2 all-new lectures that you can't find in the 2019 series at all. And so, as I mentioned last week, we'll be doing double Pyradoge for all participation, and you got your midterms back, so you realize the value of those points. And this is going to be a difficult week, so let's get started. We need to finish up last week's lecture, and we ended on the tricyclic pyridazine, pyrazole, thiophene you see here. And since you've had an entire weekend to think about it, hopefully someone can give us a thought on what disconnection might be logical here. Any volunteers before I just call on someone? How about Noor? What are your initial instincts on a molecule like this? Do we look at this molecule and we say, okay, we're going to make a tetrasubstituted pyridazine and build out the pyrazole and a thiophene? Or are we going to make a pyrazole or a thiophene and somehow forge the pyridazine together? We've learned how to make all 3 of these heterocycles. So what's your initial instinct? Don't need an answer, just thought.
Well, I think making the tetrasubstituted B ring would be sort of challenging. So maybe we'll start with the
right, something like that you probably would need, right?
Yeah.
So not so happy about that. What do you want to do?
So I would say you could start with let me see here. So can you start with the A ring that has a hydrazine at the 4 position? And then at the 2, you have the thiophene and a chloro at the 1 position. And then you could can you utilize like a sulfur oxide to do like an SNAR type?
Okay, that's very creative. I really like that. So what you're suggesting is we go through the intermediacy of something like that. We've seen that kind of chemistry before, and the benzothiophene series is a sneaky way of doing SNAR reactions on benzothiophene. I think that the disconnection you're using here is a good one, and that you're disconnecting between carbon 1 and nitrogen. And so if we riff off of this theme, I'm going to take you through a series of equivalencies. So first, I want you to imagine, can we do this? Will that be an acceptable precursor to the hydrazine?
Yes. I think in this case, you don't really need the chloro, right? You could just do like an electrophilic aromatic substitution, sort of.
So you're thinking, basically, this compound is hiding a von Richter Synolin synthesis, isn't it? So if we make this compound, this is von Richter, right? We know that it's going to cyclize there. And so this compound just comes back from this. We know we can diazotize. Is that acceptable?
Yeah.
Sorry, I have the metal in the wrong position. Sorry about that. Exactly. So we can use whatever you want, Kumada, Stille, Suzuki. Put those 2 together, diazotize. You don't even really need to do much with this intermediate. Immediately diazotize it and it will go straight to the product. And you got it first on your first disconnection. So I love the way Nora was thinking, because she made the perfect disconnection and then thought about, wait, this looks a little complicated. Can I simplify it further? Do I need the sulfur dioxide? Probably not. Do I need the chloro? Probably not. And then that series of thoughts led her down a route to something extremely simple. Perfect. Great job. So let's move on to the consulting corner that we skipped last time due to lack of time. So for this first consulting corner, we've got now a pyrazole connected to a pyrrole. And if we do what we talked about many times already, if we label this as ring A and ring B, one could look at this as simply, right? If we drew this as the problem, if the practitioner told you they had a problem making that, at this point in your heterocyclic career, you would just laugh, right? That would be a trivial compound to make. And so I want you to pretend that that pyrazole is simply a benzene ring, and let that guide you towards possible disconnections. And if we do that, look what opens up. This compound we know already from several lectures, most notably the indole lecture. It can be crafted through a variety of different pathways that involve either nitrogen-carbon breakage or maybe standard Larock disconnection. So if we do nitrogen-carbon breakage, you can imagine proposing this type of intermediate. Which is basically a Hemmetsberger disconnection. And then the practitioner tells you, oh, I already tried that, it doesn't work. So we need an equivalent to this. So the equivalent to this would be putting a halogen atom there and using some Ullmann chemistry to close it. A little copper iodide and a ligand will do the job. Where does this compound come from? Comes from the corresponding pyrazole aldehyde. And this just comes back from lithiation, quench with DMF, deep NBS, get to your desired product. You condense that with the glycine derivative. You get that enamide derivative. The enamide is then treated with copper and base, and it cyclizes closed. Then they tell you, oh, well, we tried that too, and it doesn't work. So we need to go down the Larock route. And the Larock route would basically be something like, or X here. And this just comes back from this, which is commercial. And because of the disconnections you learned in indole synthesis, this becomes child play. Now you might wonder, hey, Phil, why can't I disconnect ring A? And if we do disconnect ring A, look at what happens. Does this look like a pleasing compound to you? Do you want to make a compound like this? So it's always good to run the thought experiment. Let's say we're going to put an X here as a placeholder, and we're going to put some sort of aldehyde. You want to make that? I don't. And the aldehyde, the ester, how they put the halogen in there, right? Doesn't feel good. So it definitely makes more sense to me to pretend that the pyrazole is my benzene ring and I'm making a standard indole, rather than pretending that the pyrrole is a benzene ring and I'm making an indazole. See how that works? Great. Let's take a look at this one. This is a strange one. What are we going to do here? Well, we've got two ring systems, A and B. And this, I guess, would be one of the first intros to like a bridged kind of system, but it's not bridged because the other one is not a heterocycle, but it is kind of a weird fusion of what looks to be a saturated pyrrole connected somewhat to an amino pyrazole. So is there a trick we learned that might lead us down a road of simplification? Sung Han is staring intently into the screen and likely has something very wise to tell us.
What I think is disconnect ring A.
Okay, what happens when we disconnect ring A? We end up with an intermediate that looks like, let's just put, or PG. We'll just sketch out what he's thinking first before we get into the details of what exactly is hiding at that position. Something like that, is that correct?
Yeah.
Okay, now how do I make that?
Yeah, probably difficult.
Probably difficult, but we can keep going. We don't want to give up on your disconnection there somehow. Let's put X here where X maybe is like OTBS. And that would require that kind of compound, right?
Yeah.
Right, we would add hydrazine to that, and then we would maybe turn our X into some sort of halogen, and then heat it up, and yeah, it's not totally unreasonable. Then you just have to find a good way to make that, which could be a little long-winded, honestly. So that's great, awesome job, because you have broken ring A, which means we're going to go down the other pathway. So if we use the same logic that is implicit in Sunghan's eventual disconnection, there's an identification of that carbon as being some sort of nitrile. The first thing we can do is imagine that there's a reduction in oxidation state, giving us this intermediate. Now look what happens. This compound simply comes back. Look at what we did here. From there. So we can do enamination, of which there are dozens of methods to do that. Enamination, snapshot. And where does this thing come from? Well, this just comes back from reduced pyroglutamate. As we'll learn in saturated heterocycles lecture at the end of the week, this is a very nice building block. It's known that you can do a Wittig reaction or Horner-Wadsworth-Emmons. And this just comes back from pyroglutamate, which is cheap as chips. And how do you go to the final oxidation state? Anything will work fine. DDQ, maybe air for a little while. You're good to go. Great. So no wrong answer because you drew both. You did it during the interview and you said, I don't like that first disconnection. And then they're like, wow, that's very perceptive. And then you go the other way. You bought yourself time. And for all they knew, you knew the answer from the beginning, but you just wanted to teach them. All right, let's take a look at this one. Oh, this one is a fun one. This one comes from the outside, submitted from a person who will remain nameless and a company that will remain nameless. And they need a way of making this type of compound. In the specification that they emailed us, it wasn't really clear whether they needed the methoxy compound or they needed the pyridone, but either one is sort of interchangeable. So we'll just put this one. And the challenge with this one, not surprisingly, the reason it was emailed to us is probably because of that strange position for a fluorine. That's what ruins everything. That's what makes it a consulting question. So how are we going to make this? Well, one can imagine that you could look at a compound like this and say, well, hey, Phil, can we play the heterocyclic Vegas odds and hope that maybe if we made a compound like this, we can get some selective SNAR with fluoride, and then maybe with, maybe we'll get lucky and the fluoride goes here. We have to hope that it doesn't go here. There's some literature precedent suggesting that maybe that might be the case, but it is rather speculative, which is probably why they asked the question. SNARs with fluoride are doable, but not always the most fun thing to do, especially in a polyhalogenated context like this, where you normally use excess of the fluoride to begin with. So we need a way of thinking about this. And so what we do is we think about this from the terms of This, in my mind, is just a isoquinolone. And we go back to the lecture on isoquinolones and we look. And what do we come up with? Well, a good disconnection might simply be some sort of Friedel-Crafts reaction. So if you took a compound like this and you expose it to courteous, you would get the isocyanate. And we know in the literature that that isocyanate with further heating should happily cyclize to give you the pyridone. Well, where does this thing come from? Well, this just comes back from, obviously, the aldehyde. And where does this come from? Well, it's known that you can easily oxidize methyl groups like this to the corresponding aldehyde. And then where does this come back? Luckily, we learned it already. I think we learned it in last class. That strange pyrazole synthesis from the BMS team, process team, to give regiochemically defined pyrazoles can be used here just like we learned last time. So mix those together, oxidize up, then oxidize the methyl group to the aldehyde, do your HWE, which is known. We will send that to the person who asked the question, known actually to give the right geometry. How do you like that? Do a courteous, heat it up, and you get your pyridone. The other way of looking at this, you could say, you know, why we didn't choose this method. You could say, hey, Phil, why not try making something like this? You know, you could imagine something like this where you add in your hydrazine and you hope to get the right regiochemistry, then you do a Sandmeyer of the resulting NH2 to the bromo, but you will find that the synthesis of this compound is actually quite long-winded, and there's really not a lot of good precedent for doing that at all. Whereas all the other steps for the take a pyrazole and build on a isoquinolone are very well precedented. So whoever it is out there, hopefully this is helpful to you, and hopefully it works. And we will email you the files. Great. So let's move on to the lecture that we're supposed to be doing today, which is lecture 16. And that is purines, but more broadly, complex fused heterocycles. So these represent, you know, as close to the real world as you're going to get. They're pretty difficult, and they're kind of important in terms of things like, you know, life. So purines are, of course, found everywhere and make up your DNA and your RNA. And so nature maybe, I don't know if it's controversial to say, but this may be nature's favorite heterocycle. I guess there's some debate on that, but it could be. And, you know, there's two ways of thinking about it. Obviously, you've got A and B, and nature is thinking about this too. You can imagine that a kind of Traube-like disconnection would build a purine up from a diamino-pyrimidine or an equivalent thereof with the formic acid oxidation state that you need at that position by using some sort of formate derivative. You can also imagine that you could build this up by taking an intermediate like this or an equivalent thereof and putting the formic acid in the other side to build up the pyrimidine. Which one do you choose is kind of case dependent. And for purposes of being complete about this, there are some sporadic reports of people using triazinyl cycloaddition chemistry with intermediates like this that then decarboxylate after the cycloaddition takes place. So, but this is very rarely used. The two main ways we're going to see today are basically that. And the reason we waited for purines all the way to lecture 16 is because you have to know all the other heterocycles before you get to a purine, because each one of them is going to be evaluated from the standpoint of breaking ring A or breaking ring B. So we'll be doing a lot of that today, and we'll try to move it swiftly along, and I'll try to do a lot of it for you. But hopefully some of you are perceptive and we'll be able to join in here. Now, problem of the day number one is an interesting problem where they take formamide heat it up, and they get a purine. And it's kind of one of those interesting papers where they suggest that this explains, life. When it may be true, maybe in a volcano or nearby somewhere a few billion years ago, nature was doing this to make purine. It's possible. But what we really need to understand is, how does this thing work? So this is problem today number one. We need some deep thinker who could perhaps just opine on the types of chemistries that might happen when you take formamide and you heat it up well past its boiling point. Any volunteers?
Would you do the dehydration and maybe got a cyano or?
So dehydration means we're going to have some water around. You're also saying we're going to make some cyanide, so we maybe have some HCN lying around. Anything else?
Hydrogen?
Yeah, we're going to have some hydrogen gas come off. Anything else?
Maybe carbon monoxide.
Maybe carbon monoxide, and for good measure, maybe even a little ammonia is being generated.
Yeah.
All those
Yeah.
things are probably around there. And we're not going to go through the mechanism of this because it goes through, if you look at the paper, there's a full page on the mechanism because it's degenerate. There's a million pathways you could draw for this. No one will know exactly what's going on in the 170 degrees to create a few percent yield of purine. But what I do want to identify your attention to are the building blocks that exist in this molecule. Embedded in it are 5 hiding nitriles. So there is a nitrile hiding here, and maybe to make things easier, let's use a different color. Nitrile is hiding here. There's a nitrile hiding here. There's a nitrile hiding here. There's one hiding here, and there's one hiding here. And so if you draw arrows, you can eventually make your way to a purine by the condensation of 5 molecules of cyanide. So clearly this reaction has 0 preparative value, but it is useful to just think about a couple of things. Maybe this might be relevant to the origin of life, and maybe another thing is that heterocycles are usually thermodynamic wells, and they like to form. So it's kind of cool that cyanide can be coaxed into forming this very useful, information-rich molecule compared to cyanide, which really doesn't have a lot of intelligence. That heterocycle is pretty smart in terms of the things it can do. Okay, great. Now let's move to a series of case studies that examine purines from the vantage point of logical ways to put them together one by one. In order to do this, I think it might be good for me to go through this one as a little bit of a practice before I start calling people, but feel free to chime in if you'd like to offer a suggestion on a way to go. So you may look at this and say, well, I spy with my little eye a triamino-pyrimidine hiding in this. And so you could say, oh, what about if we took ring B and fashioned that from ring A? And so that would look something like this. And you may say, well, I just want to condense onto that trimethyl orthoformate. And the problem, of course, you're going to encounter is a regiochemical quagmire of whether it goes here or here. So your next level of analysis might be, why don't we do it stepwise? So what if we had here first NHAR, we have NH2, and we put a chloro here first? That may be a much more logical way to do it. And where do we get that from? That could come back from that. And we learned how to make species like this last time. Of course, excess POCl3 can be used on a compound like that. And this just comes back from the 3+3 disconnection we learned. straight out of the pyrimidine lecture. So certainly a viable retrosynthetic analysis. It's certainly fine. Let's take a look at the other pathway, where somehow we're going to forge the opposite mode, and we look at this and we say, it could be that you could think about this from the standpoint of a leaving group here. So we're disconnecting across this system, leaving group here. We have our N-benzylic alkylated where we need it. We need a compound like that. That X could be chloro or bromo or whatever you want. But if that X were derived from a Sandmeyer reaction, where this was a nitrogen, now we have what we learned over and over again. Oh, that is a signaling element for a nitrile. And you can imagine that this could be derived from a molecule like this, where that highlighted carbon is that highlighted nitrile. And this comes back from that, followed by condensation with something like triethylorthoformate. And into here, you would add in. Now, the advantage of that, of course, is really modular. So I can make 1,000 of these, buy 1,000 of these, add it in there, and it's slammed shut to there, and then close the other ring. Which way is better? It's totally context dependent, folks. That's why we learn both. If you only know one way, you're going to be in trouble in the real world. Okay, let's take a look at number 2. And number 2, I guess maybe is time for ask someone for help, but I won't spend too much time waiting. We'll see, maybe someone has a internal preference on what they might like to do. Do you like making aminothiazoles and building onto that aminopyrimidines? Or do you prefer to make an aminopyrimidine and fuse onto that the aminothiazole? Any knee-jerk responses? Any preferences from any of you? What feels better?
It seems like building onto A might be not too difficult, but
Building onto A, you mean start with an aminopyrimidine and then make the aminothiazole?
yeah, if you
Okay.
potentially, again, if you have like a dichloro.
Okay, let's draw that. Great idea, Nick. So here we have this. So that would require basically that we have something like we learned last time. Oops, extra nitrogen there. Something like that, correct?
Yeah, potentially.
Now, where does that thing come from? Well, you can imagine this thing comes from something like that. With our nice little chlorine there waiting for us. And this compound comes back from the same intermediate we saw above, but this time with one equivalent of POCl3. So we will take guanidine and couple it with that, followed by one equivalent of POCl3 will give us that. And now we need to find a way to put in the SCN group. So in order to put the SAN group, you have a couple of options. Option 1, so first SCN, and then 2, we need to reduce. Let's talk about those in some gory detail. For that first step, we learned one option might be just using potassium or sodium SCN, right? But there is another way to do it in the real world, which would be first, put in your SH, and second, cyanogen bromide. You can put in your SH through something like Na2S, H2S, but one of the favorite ways of doing this in industry It's just adding thiourea. So the thiourea adds in at sulfur, and then hydrolysis, the resulting group, gets you a nice non-odorous way of putting in that sulfur, followed by treating with cyanogen bromide, gives you the product. So this is a good workaround when the thiocyanate addition is not working out for you. Now let's talk about the reduction chemistry. How do I reduce a compound like this without touching the SCN? Nick, do you want to opine on that?
How would you reduce the nitro without touching the cyano?
The SCN is what I care about.
Oh, the SCN. Yeah, so if you use something very mild like I guess hydrosulfide or something, that would
You have the right idea. Yeah, a sulfur-based reducing agent. You wouldn't want to use palladium on carbon. You wouldn't want to use, things like iron filings even might be trouble. Tin chloride, maybe. But in general, the most mild way of doing these reductions of nitro groups that don't really touch any other functional group is a sulfur-based one, just as you mentioned. So sodium dithionate is the favorable reducing agent to use.
I see, okay.
But you had the right idea. You said sulfur, which is exactly what we wanted to hear. And this is a great source, mild source that's selective for electrons, where this is going to add in those to the nitro group, do that a couple of times via the nitroso, and very cleanly give you, at the end of the day, your aniline. Just a little bit of dithionate is all that's needed. Fantastic.
Could you potentially start? Yeah, sorry, I was thinking if you had potentially like a tricyclic or something like that, would that be troublesome to get the to do like a series of SNARs?
No, if you wanted it, instead of starting with this, if you wanted the dichloro one and just add one equivalent of the sulfur and then do the whole sequence and then hydrolyze down the chloro to the carbonyl, that's fine too.
Okay.
Yeah.
Yeah, thanks.
Yep.
I have a question. So
Sure.
if you start, so instead of using sodium thiocyanate, using the, your number 2 strategy,
Yes.
so installing the SH first,
Yeah.
can you reduce then and then alkylate after?
Yes, you can. That's in fact what they do. So they use dithionate on the sulfide compound, and then they take that and they treat that with cyanogen bromide, and it reacts with the sulfur, not the nitrogen, and then snapshot.
Oh, I see. So can you use that reducing agent with the SCN or?
Yep, you can use the dithionate with SCN. You can use dithionate with SH, either one.
Okay, thanks.
Yep, great question. Well, the story is not over for this little molecule, because what if you have someone who says, I really like starting with things like this. Maybe they just like compounds that are really, really polar and water soluble. This would also be potentially a viable disconnection. Probably the fastest way that one can look at this and disconnect it would be to think about installing one of these through the intermediacy of a nitro. And that's the one is a good candidate for installation through nitration, which gets us back to that. And then where does this thing come from? Well, we kind of learned this already. There you go. So dump and stir those together. You'll get out your amino-thiazole, nitrate it, reduce it, and then you're on your way as well. So both of those could be fine. I prefer the one on the right that we discussed, just because I don't need to get this very annoying water-soluble and very polar compound. But on paper, it's just fine. And who knows, in the real world, for a particular example, this may be the way to go. Question from the outside. What do we say?
Yeah, so just generally about the selection so far. Lots of Sandmeyer seasonal selection are still halogens, but are they actually used in the Metcalfe process and can be low loading and dangerous?
So the question was on the use of Sandmeyer, and a lot of Sandmeyer uses in this lecture. Are they used in medchem? The answer is yes, all the time. They're like really, really common. And in process scale, they are used. You will find a bunch of OPRDs where Sandmeyers are being used. However, as the outside person asked, it is something that you often would want to avoid. And in general, there'll be a lot of extra safety precautions that go on to de-risk such a strategy, to make sure that there's a good safety profile in doing that on multi-kilogram scale. So for process chemists, yeah, you probably would want to come up with a disconnection that avoids a Sandmeyer, but I've seen Sandmeyer used even on process scale, as long as the proper precautions are taken to make sure the intermediates are de-risked from an energetic standpoint. But yeah, Sandmeyer and Medchem, gee, all the time. Yeah, don't be afraid of Sandmeyer. It's actually really, those are really nice reactions. You don't isolate the diazo compound usually. You just make it in situ and then add your copper X to put in whatever the replacement group is that you want. So Sandmeyer is a really, really useful method that you should not be worried about using in the real world. Great question. Yeah, don't be scared of Sandmeyer. All right, let's take a look at this one, which is a very interesting one, because what we've done is taken a purine and we've deleted one nitrogen and put a carbon in its place. And this makes the story really complicated, makes it kind of difficult. So we need someone to think for us about what might be, maybe a knee-jerk response of how you could put this together. So perhaps maybe Nathan can give us any disconnection that he finds appealing.
Can you do the NH2 on the right through a courteous rearrangement? So I was thinking you're going to make ring B from A.
Okay, like that?
Yeah.
How do I make that?
That seems a bit difficult.
Well, I like the way you're thinking. This here is basically the intermediate we would need without one oxygen atom if we were to build B from A. So if we traverse, we make A, and then we forge B, that is going to need Nathan's deoxo reagent. So let's put your disconnection. We have E here, and we have E here, and that can also be a cyanide if you want, but that is just fine, because that, upon cyclization, after you turn it into the nitrile, would give you the product, you see? So in this case, the use of a courteous didn't simplify your problem, did it?
No.
Didn't simplify it, but it got me down the road of thinking about what disconnection I would need if I didn't invoke the courteous, which is just fine. So you can see here, as usual, the little latent nitrile that's hiding. And so you identify a nitrile, you identify the fact that these two are electronically differentiated enough that you should be able to make that one, keep it as an ester, and this one should be convertible to a nitrile. So we need a good way of making that. Looks great. How will we do that? Well, we just need to turn back to our imidazole synthesis chapter. Go back to your notes, take a look, and you'll see that, oh, this can be made just by disconnecting down the middle, right here. And we arise at something which is happily symmetrical. Great. So if you take guanidine and this alpha bromo carbonyl compound, just available from acetone dicarboxylate, so very easy to get. The reaction gives, on a very good day, 5% yielded product. But for a test, this is great. You can draw this in the test, it's perfectly fine. But in the real world, it simply does not work. Well, before we go back and write this strategy off completely, does anyone want to entertain the possibility that we might be able to make something like this? Anybody want to make that compound? Probably not. That's why everybody's quiet. So the disconnection of taking that pyridone and somehow building an aminoimidazole off of it doesn't look very attractive. So we need to turn our attention back to an alternative way of accessing this key building block. We'll call it A. And this key building block can be derived from a very cool rearrangement pioneered by Katritsky, wherein you can imagine that this intermediate bearing a benzoate group at the amino position can arise from a interesting rearrangement where you need to imagine that in some heterocyclic world, these two are connected. So let me show you where that leads. In principle, and this is what Katritsky found, you can take an oxadiazole, which we will learn how to make, I guess, on Wednesday. And when you treat this with base, sodium hydride to be exact, it gives you the product. How do you like that? Very cool. Where does this thing come from? Well, we just break a bond. We get to the parent oxadiazole plus our favorite acetone dicarboxylate. Reductive amination will give it to you. Where does this thing come from? Well, this just comes from a dehydrative cyclization of an acylated hydroxyguanidine. How do you like that? Pretty cool. That gives you the product in very high yield. I think it's like 70 or 80% yield. Very clean conversion to this compound, which can then be independently manipulated to give you that ester turning into a nitrile, treating that with ammonia, cyclizes to the product, and then you can deprotect that benzoate there on the aminoimidazole position whenever you like. Cool. All right, so let's move on to case study number 4. And let's label these 2 rings and go ahead and ask Brendan if there's one that he prefers us to break. Both to me look like they might be good. So which one do you want to do?
Well, what I'm wondering is if we can use like a TFA equivalent to break that pyrimidine up. Might be an easy way to get the CF3 in there.
Awesome. We already learned how to make this above. So TFAA gives you the product. Love it. Perfect. What if you want to go the opposite way? Well, that would require something like that, correct? Seems like no problem. You can add in one equivalent of amine first and the other equivalent of amine. Looking good. And this just comes back from the same thing we talked about before. Either one is good. Which one do you choose? Well, kind of depends on what your desires are in terms of substitution patterns and what you've got in-house, but either one could be fine. Fantastic.
You would add POCl3 after TFAA, right?
Correct.
And
Yep.
Okay. Nice.
Yep. Both of them would require some POCl3 action. Yep. All right, let's move on to problem of the day number 2, this interesting compound from JMed Chem, rather recent. Gee, we need some help on how we can simplify this compound very quickly. So any volunteers for problem of the day number 2, or should I just call on someone?
Can you install the trifluorotoluene ring with SNAR and then the morphine through alkylation?
Let's get rid of that. Let's get rid of that. Look how quickly simplifying that will be. And let's just imagine the whole thing comes back from that. Now, Kelly, how do I make that?
Can you go back to like the annulated thiophene with an amine and an ester?
I like where you're going with that because it's probably reminding you of a reaction we learned in the thiophene world.
Yeah, I want to do gold.
That would be a great idea. So look at how pretty this route turns out to be. One can simply take cyclohexanone, we'll get that. And then to go from here to here, we need chloroacetylnitrile, and then this compound is treated with morpholine. Brilliant. Is that what you're thinking, Kelly?
Yep.
Yep. Awesome. That's what they do. Look how quick that was. All right, fantastic. So let's move on to this one. This one is a bewildering one because now we have, we've got 3 heterocycles in there. I have no idea where to disconnect on this thing. I can, I can start with a imidazole. I can start with a thiophene. I can start with a pyrimidine. I'm lost. Can anyone help? How about, maybe the first thing I draw on the board when they're asking me the question is, I think, okay, well, I see there's a hiding nitrile here. Maybe I can buy some time and just propose something like this. Is this going to work? Please draw that out. And what do you think the reaction is from the group? They're not liking it, are they? Yeah, they're looking and saying, why did we hire this person? So yeah, way too electron rich. Don't know how you'd make that kind of crazy thing. Definitely a very poor logic being used there. So then we can imagine, well, what if we do some sort of breaking the NS bond and, maybe we can get there via some sort of courteous rearrangement. So maybe we could imagine this kind of thing. And if we do a courteous on this, you can imagine that gets you to the isocyanate, which immediately snaps shut to the imidazole. That might be okay. And then we have to think, well, where does this thing come from? And then we can say, oh, well, that looks like it might be Kelly's logic again. Where we can walled it shut. Or in this, yeah. E there. So that might be okay. That one is potentially reasonable. And we just need a way of making that pyrimidine. But an alternative approach would be to think about building this up in the opposite mode, again, taking advantage of that hiding nitrile. So first one could imagine we have an imidazole, we have thiophene, that maybe comes back again. We realize there's this, so maybe that comes back from this compound. That's looking pretty good. You can imagine that that again will work, no problem. And where does this thing come back from? Well, it turns out you can do selective cyanation of this compound. And this just comes back from imidazole. So yeah, which is the way you would use. I would say that this strategy, given that you could find a fast and simple way of making that amino-nitrile pyrimidine, which may not be that straightforward to make quickly, could be okay. But perhaps the fastest way to make this would just be thinking about starting with the imidazole and making your way down to the end.
I have a quick question.
Yeah, what do you say, Noor?
So I sort of have a crazy idea. I don't know
Yeah,
if it's
I want to hear it.
or
What's the
not.
crazy idea?
So if you start with the biaryl AC ring,
Oh, I love that. Let's draw that out.
and then a protected amine,
Okay.
and realizing that realizing that these are enamine type, if you can introduce an electrophilic sulfur.
That is very clever. So that's the kind of idea that I think, I mean, it's a really good idea. We should give you a bunch of pure dose for that one, because on paper it looks reasonable. And so in order for me to suggest it to a group, I would just want to I would want to see if there's anything. I would search on SciFinder, perhaps instead of a pyrimidine, just a phenyl, and see if anybody's done such an annulation. Maybe just make this a pyrrole instead of a imidazole. Look for similar types of reactivity to give me confidence that this has a chance of working, because it does commit them down a certain road that they have a hard time getting out of if it doesn't work. I guess the backup plan for your very creative approach could be to install at those positions maybe just a intermediate NCS or NBS step, and then nucleophilic sulfur. But I love the idea. It's very creative. Yeah, definitely suggestible idea. And one that we have never heard before. That's great. Love it. Thanks, Noor. That was awesome. All right. So let's move on to number 6. And this one, again, instead of one side being imidazole, we have sneakily threw in an extra carbon at this position. And this happens all the time in medchem. I'm going to show you some real world problems in just a moment where they don't know what they want. So they give you a heterocycle or a bicyclic heterocycle, and the worst problems are where they give you one structure and they put X all over the ring. And they say, oh, X could be carbon or nitrogen. So their one problem explodes into 16 different problems because they're putting all the substitution you can imagine. And every single one you do is a different type of logic. So replacing a carbon for a nitrogen and vice versa often leads to completely different logic. So let's draw the rings and see if anybody wants to opine on what they think might be a good way to go. Let's see, maybe we can hear from Daniel. Any initial thoughts? And if Daniel's not on the line, perhaps Carter.
Could we treat the pyrimidine as just an aniline or a diamino?
Aha,
Isoquinolone?
You're thinking Bischler, aren't you?
Something like that, yeah.
Now that you've drawn it out, any issues with it?
Well, it doesn't look so great on paper.
Why not?
Thinking you'd probably have selectivity issues.
I'm thinking as soon as you liberate that nitrogen, maybe it came from a nitro or maybe it came from something else. As soon as that's liberated, you're going to get some sort of cyclization to give you now a pyrimidino pyrazine.
Yeah.
So you may say, hey, Phil, well, why can't we just use, O-methoxy here and then turn it into an NH2 later on? And perhaps that would work. Maybe. You need some sort of equivalent to that NH2 to avoid the pyrazine ring formation from happening. But you've given us a great stepping point now to move on because we've done the take B and annulate A. Now we need to find a way to take A and annulate in B. And if we do that, we immediately identify the hiding nitrile here. And we say, well, let's just draw that intermediate out. We've got our R group here where it was before. We have our pyrrole. We've got the nitrile that was hiding there. And we've got our amino group there. The amino pyrrole is stable because it has that nice electron withdrawing group. Otherwise, it would polymerize pretty quickly. And now we have to find a way to quickly put that together. You may say, well, could this come back from that type of species where you somehow get that to add in and you hope that's going to add in? That's not a very good disconnection because it's not really nucleophilic enough at that position to add it back into that nitrile. So we need to do something a little bit different. And the different thing we would do is again recognize that there is a hiding nitrile here. Let's take a look. Hiding nitrile right there. So let's make a disconnection based on the hiding nitrile, which would involve simply taking condensing those two together and then treating with base, and out will pop your amino pyrrole. Where does this thing come from? Well, I think we learned this in a past class, but just treating that with trimethyl orthoformate will give you your vanilligous ester, which will then condense very nicely with your amine and then cyclize. Cool. All right, let's move on to
for the rigid selective cyanation, just in the problem above, would you use
problem 5?
If you go left, if you go to the left, so for that one, would you use copper cyanide or something?
Yes, that's what they use. Yes.
So is that because of the directing effect of the protecting group?
I think it's an electronic effect wherein the way you can rationalize it is for the same reason that this will undergo halogen metal exchange faster is the reason that it will also couple faster. It's more pyrrole, C2 on a pyrrole like.
I see. Okay.
Yeah. Yep. Good question. Whereas, oxidative addition into this one is more enamine like, and so it should be slower than this one. But that's, great question. All right. Let's move on to this beautiful work from the Eschemoser group back when he was at Scripps, collaborating with Ram Krishnamurthy, who's still here, a very brilliant scientist. And Eschemoser was, of course, obsessed with this idea of wondering why it is nature chose the building blocks she chose, and the way she chose them, the so-called, as he called it, chemical etiology. And as part of those manifold studies, one of the things that he and his team looked at were these kind of origin questions of purines. And this type of diaminopurine, for example, why does it come why does it emerge this way, as shown here, and not this way? So if you took, let's say, cyanamide and this aminoimidazole and condensed it with them together, you observe that product. But the question he wanted to know is, well, why exactly is that? Why is it that the nitrogen doesn't attack instead of the carbon? And so as part of those basic studies, you can read the original papers. The team set out to actually make what would be the product of the purple union between cyanamide and aminoimidazole. So they needed to prepare this compound from scratch, and it's a beautiful case study of how you can make these types of ring systems going either direction. So we need some help here on some thoughts on what we might do to put this together. Let's say we'll have A going into B and B going into A. Anyone want to sort of pontificate on one of these potential routes? Maybe maybe Junchen?
Yes, I saw some hiding symmetry here.
Aha, where did you see that?
The B ring.
B ring, there's some hiding symmetry in the B ring. And so you want to take B and annulate on A.
Yeah.
And how would you like to do that?
Just treat with some C2 equivalent, such as acetal, and then cyclize.
Now, the only issue with this problem is that it has been misdrawn. I didn't catch this. Sorry, guys. So I'm going to get to, we're going to do this one because I want to do this one, but we also want to cover the one that Eschenmoser actually did. So the one that we should be looking at is actually this one, but the erroneous structure is a great opportunity to study that one as well. So this is what we should be studying here. But guess what? We're going to do the other one too. So it's great that this happened. You're saying take triaminotriazine and simply couple that with, let's say, acetaldehyde. Yes?
I guess you have one more carbon, right? It
Well,
should be
the two carbons I need are here.
Oh, sorry. Yeah. That's
You're good. You're good, Junchen. And you identified the symmetry. That's fantastic. Now, the other possible way is imagining that you've got an aminoimidazole like that. And now we need to couple it to something that looks like this. And indeed, that will work. So you can take diacyanamide like that and couple it to this aminoimidazole, and it will give you the product, which is great. Maybe we should retain this error in the next class too, because it's a great segue into the real problem, which is this one above. So if we use the same logic, look what happens. Same exact logic. Now we start with the aminoimidazole of the type that I drew below. There's our aminoimidazole, and we need to react that again with, let's just put this compound A. A will give us our product. And that one simply comes back from nitroimidazole. So the same logic. Now we have this bonus isomer that we've got here in the 2021 lecture. But now what happens with our, what happens with our Junchen-like disconnection? So Junchen, we can't do that symmetry thing anymore, can we?
I think we can still, right? Because it's
okay.
symmetry.
He's insistent. Okay, that's good. Now we just need that, right?
Yeah, that looks good.
That looks pretty good. And where does that come from? Well, guess what? 3 plus 3. So you can imagine taking NaCHO here, E plus this really fun reagent. This is called Biguanide. And it needs to be prepared fresh before you use it. Biguanide comes from simply taking urea, converting it into this compound, and then adding in guanidine. That will give you a solution of biguanide that is very strongly basic and nucleophilic and can react with the ester you see there to give you Junchen's intermediate. So we see how this logic worked for both the erroneous isomer and the one that we're supposed to cover up here in a fortuitous fate of good luck. All right.
The dicyanamine, is that a stable compound?
Biguanide?
No, the A, the compound
Yeah,
A.
yeah, you can order that. You can order that from Aldrich. Yep.
And they make it presumably from just chloroamine, or?
I believe you can take cyanamide, and two ways of making that. You can take cyanamide plus cyanogen bromide. I think that's the way you make it. You deprotonate the cyanogen, you add in cyanogen bromide, and you get the sodium salt of diacyanamide. I believe that's what.
I see.
But you
Okay.
order it. We won't make you make that.
Yeah. Thanks.
Yep. All right, great. Let's take a look at some other examples from Eschenmoser's work. Here's one that should be a rather quick one. Problem number 8. You can imagine this one arises by, again, taking a look at that as being a hiding nitrile. And so we get back to our same intermediate that we had before. We have our amino-midazole. And we just need a nitrile. So you can make that compound. And we also need access to this species. So how do we make that? Well, again, we can look at this as being nothing more than maybe an isocyanate. And so you can imagine that, again, we start with amino-midazole. And we convert it into NCO. And this little fragment here comes back from that. So I believe this is a series of back-to-back Orglet papers on the syntheses of all of these various little interesting little purine derivatives, and might be Eschenmoser's only Orglet papers. So really, these are really fun reads. All right, so let's move on to our late-breaking consulting problem. This one just came in from a company that will remain unnamed, from a person that will remain unnamed, and their request was for a 100-kilogram synthesis of that compound. So this one should be very straightforward to come up with potential disconnections for, based on everything you learned. So there's a real late-breaking problem from a company which I assume they're on the line waiting feverishly for your answer to solve their problem. I guess the interesting question from an IP standpoint is, once we put this in the public domain, is it still patentable? I guess because we didn't enable it, it might still be patentable. So these are just speculations and ideas, these consulting corners. They don't represent enablement. Yeah. Oh, I just got demonetized? I didn't even know we were monetized.
No, we're not
What do you make, 10 cents per month on this thing? Oh, what do we have, 50 views a year? All right. Yeah, who's watching out there, really? Not many people. Okay, it's a small community. All right, so I've made my jokes, given you plenty of time to think. And So
Can you start with the 3-cyano-2-amino pyrrole? Would that be stable?
why do you want to put a cyano in there?
Oh, whoops. Well, my thought was to oxidize that. I guess you could start with the ester as well, and then use like some like thionucleophile to close it up again to make the A ring.
Yeah, I mean, if you have that compound in hand, you just need formamidine acetate and you're good to go. Right? Now we just need a good synthesis of that compound. And R can be H. We need a good way of making that. I mean, there's two ways of sort of skinning this cat. You can imagine that maybe there's a hiding nitrile there, and you could say, well, could we make it from something like that? But maybe more logical would be to look back and say, well, you probably could make it from something like this. That, upon treatment with tosic acid, would probably give you your product right away. And this just looks like a derivatized amidinyl malonate. And it turns out, if you look at the patent literature, you can actually make that pyrrole that way, wherein the attack takes place here, and then tosic acid gives you the product. So, Tim, you got it basically in a millisecond, right? The next part of it was just going to SciFinder, but the key disconnection, you got it. But let's say these people who are listening on the line say, oh, of course we know that. That's not a good suggestion at all. We don't want to do that. Is there another thing we can think about doing? Well, we'll have to go the other way. So if we go the other way, it means maybe we can annulate on just as if it was an indole. And we use our same aminoaldehyde equivalent building block. And that might work just fine for you. If you don't want to use the aminoaldehyde building block, you could also imagine there is good precedent for taking a compound like this and converting it into the corresponding amino derivative, and then just cyclizing Bischler style. Also okay. Where do we get this compound from? Well, one equivalent of POCl3 after the addition of formamide. So cook up formamide, dimethylmalonate, we'll get the corresponding OH here, and then POCl3 on that, one equivalent, will give you your chloro compound, and then add in and do a Bischler that way. Both these routes look reasonable. And if this were a consulting session for this process group, where they gave no indication of what they had tried before, these would be the first two things I would start off on. And then they would tell me how they maybe tried all of this and it doesn't work and they need a totally new suggestion. And if that happens, please email us. And then maybe we'll come back and revisit this failed potentially consulting problem. So hopefully this is useful to you folks at whatever company you're at. All right, great. Let's move on to Levitra. And this is an interesting little compound because it can be broken up in either a very, very bad way or a very, very good way. The difference between the two is rather striking and exciting. So let's talk about the bad way. What would be, let's say, a disconnection here that would be rather complicated?
Forming an NN bond.
forming the NN, just tell me the disconnection. Do you want to take a fully formed B-imidazole and put onto that the triazonone, or do you saying to make a sort of triazonone and then forge the imidazole? What was your disconnection?
No, I was saying that I think a bad disconnection would be breaking the NN bond there. So I guess
if we
that
break
would
the
be-
NN bond, okay, good. If we break the NN bond, what I'm to infer from that suggestion is that it must mean we're starting with this. Because this is the only disconnection I can think of that would require NN bond synthesis. This is what you mean, Brendan, correct?
Yeah, I guess so.
You don't sound that convinced, but that's I'm breaking an NN bond by doing that,
Yeah.
right? And then this compound plus AR nitrile will give me my product, right? Where the nitrile carbon is that carbon there. Now, why is this such a terribly bad disconnection? People make NN bonds using electrophilic nitrogen all the time, even on scale, as we will learn about on Wednesday. But why is this one in particular so problematic? In this amination step, Brendan, is there anything you worry about?
I mean, I guess the regioselectivity.
Yeah, I got these two nitrogens here. Any idea which is going to aminate first? I mean, it's a crapshoot, but I would bet the wrong one, just based on what we know about alkylation, where the ester usually directs the mesionic intermediate away. So if anything, you're probably getting the wrong regioisomer. So that is a horrific disconnection, as you anticipated. Alternatively, we can look at this compound and say, well, this little imidazole here is really just a hiding dehydration, isn't it? It's just a dehydration. And if it is just a dehydration, look what happens. Wow, look at that. So I've gotten rid of the complexity pretty quickly here. Now, how do I make this thing? Now we're going to look at this very carefully, inspect it with a microscope. And if we look at it really carefully, we see, okay, there's a nitrogen, there's that carbon, there's another nitrogen there, there's that. And I remember that Phil told me I could make things like that, which are called amidrazones from a nitrile. And so if I just excise all of it, I end up with something that looks like that, which is my amidrazone, which we know we can get from the nitrile plus hydrazine. And then we are left with the other half. And we take a microscope and we start looking at that and we say, okay, well, here, this is an ester. That here is going to be a carbonyl. And we end up with an alpha keto ester. And you're done. How do you like that? All right, so that's how they make Levitra. Let's take a look at this interesting compound that is used for chronic heart failure. And in this problem, I'm going to give you a taste of what they're asking in the real world, which is, again, what I mentioned before, these vexing problems where they come and they say, we don't know if we need the pyridine or the pyrazine, so just figure it out. Those are fun. So let's do the easy one first. Let's do X equal to carbon, because at least it's a little bit, there's less to worry about there. So is there an initial disconnection for this one that you can look at and say, I'm going to break this down in the middle to dramatically simplify it from the get-go. Is there some piece of this molecule that begs, please disconnect me?
You could start with the chloroketone.
With the, you're talking about the chloroketone, you're talking about the indazole part. Is that right?
Yes.
Okay, before we go down that route, Nor, what do you want to do about this stuff over here? Where is that coming from?
You could do cross coupling.
Oh, cross coupling with the triaminopyrimidine, and then the indazole as well. And that boronic acid, that bromo, gee, that's going to be a difficult Suzuki.
Or maybe you can have an ester as a handle for later condensation.
Yes. So you've identified the key disconnection, which is we want to go back to you can take this and convert it into the amidine, and then the amidine can be reacted with this diaminonitrile, where this here is a protecting group for the nitrogen, this protected diazine. So that's what they do. But you made the key disconnection, you cut right down the middle, and now we have a compound like that. Now you mentioned that this might be derived from this. That's your disconnection, Nora, right?
Yeah.
And I love it. I think it's great. Put that on a test, you get full credit. That's not what they did. They instead took this in a very different direction, presumably because maybe of the intermediates they had lying around, but they decided to actually build up the pyridine nucleus. And they did so by way of this amino pyrazole plus that. And this compound comes back from that. And they get perfect regiochemical outcome on that. They then do their Friedel-Crafts cyclization. You might wonder why they don't just do this. I'm not sure. I think your disconnection, Nora, is great. That's certainly what I proposed first, but I'm just showing you what they did. All right, now all the trouble starts. All the trouble starts when we start thinking about the other nitrogen. So I'm going to put that other nitrogen, I'm going to overlay it in the same structure so we save time. I'm going to put the other nitrogen here, and I'm going to put a bromo here, which is what they use as a precursor. So how do you make that? Well, let's simplify it a little bit further and just say, you know what we need is something like this. How do you make that? Well, you may say, oh, can I get it from something like this? Maybe. Add that into hydrazine and then Sandmeyer it off. Certainly the first thing I would propose. That's not what they did, though. What did they do? Well, they got it from this compound. And this compound is the product of problem of the day number 5. There you go. This MedChem program was initiated apparently based upon this interesting rearrangement that they found in the literature that leads very rapidly to this heterocycle. This one is super easy to imagine how you might be able to access it. And so now all we need is a way to rationalize heating that up with hydrazine gives this indazole-pyridazine. So what happens when we treat this with hydrazine? We have 6 minutes remaining in this lecture. Still a lot to go through, but hopefully someone can guide us as to what might be going on.
Yeah, so your hydrazine would add into the ester.
Okay, then
And
what's
then that nitrogen could attack alpha to the, or C2 to the sulfur. Yeah, exactly. And that would probably cause you to open up your thiophene.
okay?
And
Now what?
then you'd probably need another equivalent of the hydrazine. Or, well, I guess you would first automerize. Yeah. And then that equivalent of hydrazine could add in, and you would lose both ammonia and H2S. Yeah, so then you would get the second addition.
Pretty awesome. Fantastic job. That's great, Simona. You know, the other possible mechanism that one can imagine is that this compound that you get here decides that it would like to fragment instead. So you can imagine that this thing opens up to that's another equivalent mechanism that you can't rule out. And all you need to do to go from here to the product, by the way, after you lose ammonia, is an oxidation, which they suspect happens with air. So here's an example of where, you know, you're doing a medicinal chemistry program and you notice a paper like this in some old journal and you say, wow, that would fit really well into the current program I have, and it works much better than finding a way of making this, which is actually not very easy. This is the logical disconnection. This is not a logical disconnection in problem today, number 3 here. 3 or 5, I don't know what the numbering is, but this problem today is not logical, but it's one of those things you found in literature, like, wow, I can use that. You definitely wouldn't come up with this based on first principles, certainly not.
Hey, Phil.
Yeah.
Do they comment whether this happens with other 5-membered heterocycles?
I don't think they exemplify the Purine or the pyrrole, but I bet the Purine would work too.
Okay, thanks.
It was the same kind of chemistry as we learned in the Purine lecture. You can open those up too, but I bet Purine would work too. All right, great. Well, we are pretty much right on time because I don't mind this bleeding over into the next lecture. We've got 3 consulting problems from the real world, and we need to figure out a way of making these compounds in the most logical fashion. We've got A and B here. And so you may look at this and say, well, could we potentially take a pyrimidinone and build on the pyrazine? If we do that, look what happens. Let's say here you've got ester, and here you've got an X, and the hope would be that if you add in hydrazine to that, you get the product. But does anybody want to make this? Ellie, do you like that compound?
No, it seems pretty complex.
Yeah, doesn't feel good. So let's just make a disconnection that feels a little better. So we can imagine that first, maybe we can simplify this to the corresponding dichloro compound here. And if we treated this with ethyl isocyanate, it should attack there and then subsequently do an SNAR. And this compound just comes back from this. And the key here, the reason I'm doing this instead of a nitrile, is to teach you a sneaky trick that can be used when you're worried about competitive SNAR on a molecule. So you convert this to the thioamide with something like losocin. And then you can use Boger's method with silver and ammonia, which is very mild room temperature, that will cleanly take that sulfur into an amidine. If you were to propose the addition of morpholine with strong, with heat to a compound like this, the medicinal chemist may complain about SNAR potentially occurring there. But if you start from this discrete compound, exchange the sulfur, and then turn it to the amidine, there are no complaints going on. If you insisted upon using the nitrile, you could take this compound and treat it with dry HCl, which would lead you to a compound like this. And then perhaps when you treat that with ethyl isocyanate, it gets you to this compound, which subsequently you can maybe do your SNAR with.
Hey,
Okay.
Phil.
Yes.
Sorry. Really quick question. Could you, for this, could you potentially do a Thiazole with the tetrazine and like an enamine?
The Thiazole with the tetrazine and enamine is a interesting idea, but you would require that you had the same, that would give you the ester grouping here. You would have the ester you need here, and then let's say methyl there to get this. That's an interesting idea, with this coming from, that's commercial. We learned that one already. Plus something like, well, we need, we need something there. Yeah, if you just have the enamine, you're going to lose the amine when it rearomatizes. So you need some placeholder here. So that's the problem with that one.
Okay, thank you.
Yeah, no, it's a good thought. I'm glad that you thought immediately about a tetrazine cyclization. Definitely a good idea. But I'm having a hard time finding the right component here in order to make that go without just losing that in the product. You know, normally when you use a tetrazine cyclization, the enamine is sacrificed and the R group here is retained. So, you know what might work? Okay, remembering back to Boger's notes. Okay, how about that? That may do it for you. Yeah, we may be able to resurrect that for you. That might work, Carter. Yeah, if you propose that in a test, I think that's fine.
Or maybe could you use a methoxy and then convert that into then deprotect it.
You say that again, Nick. Use the what?
If you use oxygen, yeah. So basically, I had a similar idea.
Yeah. Normally, it's difficult to use the oxygen. Normally, people use the sulfur as a leaving group.
Okay. Okay.
Yeah.
Thanks.
That's normally the tactic that Dale uses. Great. Well, we have a couple little consulting problems to go, but we are already over 2 or 3 minutes, and I don't want to carve into your other time here. So we will see you on Wednesday to continue this, as well as begin. I keep promising it gets more complicated, but next time it really does get more complicated. Maybe the most complicated. I think it's the most, yeah. Next one is, I promise. I promise next one is the most complicated, and then it becomes easier and easier. How do you like that? So get ready, have your coffee, go on a run, do something to get yourself ready for Wednesday morning. And then we also have a guest lecture on Wednesday later in the morning. So, all right, folks, thanks, and we'll see you in a couple of days.